Hey folks, okay, well, last time around we talked about the three different techniques we can use to generate scanners for our languages. So either a table-driven approach, direct-coded approach, or a hand-coded approach. So what we want to take a look at today is the table-driven approach to generating our scanners. So again, the idea is we'll have one stock algorithm, one stock set of source code, if you like, that works for any language. And what we'll have are three different lookup tables, and we put different data in the three lookup tables that's language specific. So once we've got our scanner code written, all we have to do if we want to create 10 or to recognize 10 different languages is to create 10 different sets of tables. So the three tables that we're going to use in this are one, to classify the different input characters that we can see. So for any programming language, there's going to be different sets of characters that are relevant in different situations. So, our identifiers might be lowercase alphabetic, or they might be just purely alphabetic, or they might be, alphabetic plus underscores and whatnot. We might have a bunch of characters that are used in math symbols. We might have the digits that are used in integers or as part of floats or whatever it might be. So we've got different sets of characters that are relevant in different ways. So what our input classification table is going to do is say, okay, you'll have let's say a row for each different character, each different possible input character, and then the lookup value for that will be what kind of character it is. So you look up in there, look at row A, and it tells me, that's or the row for the lowercase a, for instance, and that's going to tell me, it's a lowercase alpha. I look up lowercase b, it's going to tell me, it's a lowercase alpha. If I look up, the uppercase b, it's going to say, that's an uppercase alpha. So just one big table that tells us for each possible character what type of character that is. And again, the type is based on whatever's relevant to the finite state machine. So we've got a classifier, and then we'll have a transition table. So this table is going to be used to go through and say, okay, if I'm in state whatever, and I see a character of this type, right, based on the classification types we had, what should my next state be? So transition table, what kind of character am I looking at? What state am I in? Tells me what state I'm going to be in next. And then finally, a token type table is going to tell us, for the state that I'm in, what kind of token am I looking at, if any? Right? If this is the state I stopped in, what kind of a token must I have seen, if any? So these will be the three different tables that we're going to generate and make use of in the algorithm. So, for example, let's say this is the kind of token I'm interested in. The tokens that I'm interested in start with an uppercase letter, and then they're followed by one or more lowercase letters. So the kinds of characters that I'm interested in are uppercase characters, uppercase alphabetics rather, and lowercase alphabetics. Right? Those are the two different character types, and then anything else is pretty much something that's just going to be a reject, if you like. So for my classification table, I'm going to have, a row for each of the lowercase letters, and that, if I look up that row, it's going to tell me, that thing's a lowercase alpha. I'm going to have a row for each of the uppercase alphabetic characters, and it's going to just tell me, that's an upper alpha, and anything else is just going to be an other. Now, in all likelihood, what we'll do is see if we can find a way to collapse these tables, but that's an issue for another day. The simplest form, we just have one row for every single different input character that we're interested in, and say, okay, what kind of character is that? And then for the transition table, we're going to say, okay, for those different types of characters, right, lowercase alpha, uppercase alpha, and anything else, other. So we'll have a column for each of those character types, and we'll have a row for each of the states in our finite state machine. So let's say this was our finite state machine, right? We've got our start case. If we see an uppercase alpha, then we go to our new state where, okay, I've seen an upper, but I haven't seen a lower yet. And then if I see a lower, I get into my accept state, and as long as I keep seeing lowers, I stay in my accept state. So my transition table is going to have each of those states and kind of a default reject state that, anything else takes us to a reject. And again, I just say for each of the different kinds of character, for each state, where should I go next? Right? If I'm in S0 and I see an upper, then I want to go to S1. Anything else should take me to a reject. If I'm in S1 and I see a lower, that should take me to S2. Anything else should take me to a reject. If I'm in S2 and I see a lower, then I should stay in S2. Anything else should take me to a reject. And once I get to a reject, I just stay there forever. And then as far as our token types, if I end in an S2, I've seen one of my identifiers. If I end anywhere else, I haven't seen a valid token. So this is what our three different table types would look like. Now, the reason for having the three different tables instead of just having one giant lookup table that told us everything would be to try and minimize the size of each table. So if you've taken the database course, then you've looked at database normalization to try and improve the performance when you're accessing each of the different tables. So reducing memory costs and thus improving paging, improving cache performance, and that kind of thing. One of the issues with this is, as I was saying with that last table, if we've got, in our input classification table, if we've got one row for each different possible input character, that might be practical for something like, ASCII, where you've just got 128 characters basically. But if you're looking at Unicode as the language for your source code, right, for the language that you're recognizing, then that table would be massive. In that case, it might make more sense to replace your input classifier with actual function calls instead that said, look up, and it might even be the case that you use a table where some of the entries say, if it's one of these things, go off and look up with this other function what should happen next. So you could very well wind up using classification functions instead of a table, which again is one of the reasons for the direct coded approach that we'll talk about in the next session. But what we want to do if we're trying to automatically generate our scanners is to automatically generate these tables, right? For this one, the general code for the algorithm is fixed. It's these tables that we have to auto-generate. So what we'll do is for that transition table, this is the really interesting one for us. What we'll do is start off with, we'll have our set of states. So we've got our 4 states for the DFA that we begin with, right? The 3 states and then the reject. And we would have a separate column for every single one of the characters in the alphabet that we're dealing with. And so what we'll do is as we go through our DFA, we'll fill in those tables, right? We'll fill in all the entries in this table. And remember, this is during the process of generating our scanner. So at that point, we don't care so much if our scanner generator is a little slow or creates these big tables, because it's not the one that we're going to be using later. It's just being used to build the scanner that we're going to use. So for that one, we don't care too much if our transition table temporarily gets huge. So we'll let this thing get really big. We'll have a column for every single letter that we're dealing with. And once we've filled it in, if we see 2 columns that are identical, then we can collapse the 2 of them together. So for instance, if we see lowercase a and lowercase b are the same, then we'll collapse them into one that covers a and b. And then if we see that lowercase c is also the same, then we'll collapse those together. So we'll gradually build up these character sets. And the heading for each column, if you like, identifies one of these character sets. So this is the column for A, B, and C. And as you keep going, this is the column for A, B, C, and D. This is the column for A, B, C, D, and E. So you gradually build up as you're going through this process, again, collapsing equivalent columns. And then as you're doing that, you use that information to build your input classifier, Once you realize that A, B, C, D, and E all have the same effect, then you create a class for those in your classifier table and say, those 5 characters create a group. Right? You create an entry in your input classifier for those. So as you go through collapsing your transition table, you can go through and form your input classifier. And that way you can get a relatively efficient version of each. And of course, the token type is relatively easy to go through, right? If we've got our DFA and it's got each accept state labeled with, okay, this accepts this kind of token, this accepts this kind of token, then we're just going through, and for each of the accept states, we're putting in an entry for that type of token, and everything else is invalid. So again, we can go through from our DFA and just gradually fill in all of the entries for all of our tables. So, and again, this is basically reiterating what I just went through: how we go through and create the transition table, how we create the classifier table, how we create our token type table. That. So then we need the algorithm to actually go through and use those tables to simulate our DFA. So we'll have an initialization step at the beginning where we set everything up before we start running. So we'll keep track of the current state, and we'll start that in our S0 state. Our current token, so this is the set of characters that we've read so far as we're trying to process a token. So we'll start that off at the empty string, and then we'll have a stack that is going to be used to remember which accept states we've gone through while we're processing these things. So that if we wind up, if we go past an accept state, we can back up to it. So we'll have this stack that keeps track of the accept states that we've seen. And I'm just going to push a special character on the bottom of this thing. So I'm going to call it end or bottom. And then we get into the algorithm. So what we want to do is roll forward, simulate our DFA as far forward as we can. So as long as it doesn't take us to a reject state, we'll read the next character, append it to our token. Okay, so that should probably be a TOK. Append it to the token that we've built up so far. If we're in an accept state, then clear the stack and push that on. Look up the character type in our classifier table. Given the character type and our state, then go to the transition table and look up what our next state should be and update that. So we're just going through this cycle of saying, okay, if I was in an accept state, remember it just in case I have to come back here. Look up what kind of character I've got, look up what my next state should be, and go there. And we just keep going as far as we can. So if we get through this and where we wind up is not an accept state, right? If we kind of go past an accept state, then we want to back up to the most recent one and say, okay, that's the kind of token I'm going to think this is. So if I've gone too far past an accept state, then I think I used end in the initialization. So while I haven't hit the bottom of the stack and I'm not in an accept state, pop the top state off of the stack into S and chop the last character off the token and roll back one character in our input stream. So eventually we can go back and look up what our token type happened to be. So we've got a nice straightforward algorithm to go through and essentially work forward as far as we need to and roll back if we need to. So this is good. It does allow us to kind of scan forward and roll back when we need to. But there are some efficiency issues with this one. So one of the things that you can run into is if you've got a really long string and you're reading all the way to the end of it because you want to read as far as you can, but then you have to back up a long way to find the last time you were in an accept state, then you might wind up doing that over and over again, reading a couple of characters that take you to an accept state and then reading a whole bunch more that don't get you anywhere, and then you back all the way up. And then maybe from there you pick up and read a couple of characters and that gets you to an accept state, but you have to read a whole bunch more all the way to the end that don't get you anywhere, and you back all the way back up to that last accept state. And you can wind up doing this over and over and over again. So in this particular example, the regular expression says accept anything that's either an xy or I believe that should be an xy star or a z. So an xy. Oh, sorry, that plus. Clearly, it's too early in the morning. Any sequence of one or more xy's followed by a z, or just a single xy. So you can have a whole bunch of xy's, and then a z, or just an xy by itself. Oh my goodness, it's too early in the morning. So if I get this string xy, 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 then it doesn't end in a z, so this xy plus z can't possibly be what we're interested in. So the only thing it can accept is the xy. But again, what's going to happen when we simulate our finite state machine is it's going to go through, and again, this is basically saying if I see just an xy, I'm in an accept. If I see a z, I'm in an accept. If I see a bunch more xy's and then a z, then I'm okay too. So this DFA is essentially recognizing this expression for us, but if I get this whole long string of xy's, then all it's going to be able to do is to pull off one xy at a time. But each time, it's going to have to read all the way to the end and then back up. Right? So it's going to read all the way to the end of this and then back up to that first xy. And it's going to say, okay, I saw an xy. And then it's going to start from there and read all the way to the end and then back up to that first xy. And etc. You get the idea. So this can be quadratic in the number of characters in your string here. So what we would like to do is to try and prevent this huge rollback problem where we're over and over again reading this great long collection of characters that we can't make use of. So what we're going to do is add an extra table that says, okay, let's make a note. If I'm in a particular state and I get to this position, don't bother looking any further because I know that's kind of a dead-end state. It can't lead me to an accept. So what we'll do is this first time through the string, we'll go through and read the whole thing. So once we go all the way through, and so we go through our x, our y, our xy, 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 and we wind up here and we're at the end of the string and we can't do anything. And we say, okay, so if I get to this position, if I get to the end of this string and I'm in this state, then it's useless. And I'll start backing up. And I'll keep backing up until I get back to an accept somewhere along the line. But each time I'll say, okay, well, if I'm in position 7 and I'm in this state, then I know I can't get anywhere from here. This is a useless state. If I'm in position 6, so I just keep backing up. So I'm unwinding this string, going the opposite direction to my arrows actually, and keep backing up and saying, okay, well, if I'm in this state and I'm in position 6, if I'm in this state in position 5, if I'm in this state in position 4, I'm in a useless spot. I can't get anywhere from here. So as I back up through this, I remember which states from these positions were a useless state to me. So that's fine. Then I eventually accept that first xy, and then I start reading the second one. And so I pick up the second one, I see my x, I see my y, I say, okay, things look good so far. I read that next x, and I get here, and I'm in that position where I said before, oh, geez, if I'm in position 4 and I'm in this state, I can't get anywhere from here. So at that point, I can short circuit this and say, there's no point in me trying to pursue this any further. I know this isn't going to go anywhere. So after that first pass through the string, I back up and say, okay, I know this is a useless path to me. So the next time I come down this path, I can stop there. So this is called a maximal munch scanner. And so again, what we're going to do is keep one counter I to keep track of what character we're in our input stream. And we'll have a table that keeps track of if I'm in a given state and a given position in the input stream, do I already know this is a dead-end state? So initially we'll say, well, it's false for all of them, right? We don't know any of them are dead ends in the beginning. So we initialize all these things to false. And as we go through the algorithm, in that rollback section, that's where we'll go through and say, if I'm rolling back through an input position in a particular state, I know that's a dead end. So our revised algorithm, again, pretty much the same as before. Just we'll keep track of, we'll initialize that transition table, or pardon me, initialize that failed state table if you like, and we'll initialize our position in the input stream to 0. And then we'll go through and do that same sort of idea. We'll read the next character, concatenate it to the token, increment the position that we're in, and check and see if that failed table says this is a dead end. If it is, then there's no point in continuing on reading more characters. We'll just jump straight to the rollback section. Otherwise, we'll go through our algorithm normally. And what we'll do is keep track of both the state and the input position that we're in when we push things on the stack. So our stack is just a little bit different because it's got the positions remembered now too. And then for the rollback, again, as we're rolling back, we also update that table. So as we roll back looking for the most recent accept states, all of the things that we roll back through, we say, we update that table entry to say it's true, this is a dead end. So we pop the elements off the stack, update our stack and our position, and chop the last character off our token and just roll back as far as we need to. So this is, again, just an optimization to try and prevent unnecessary reads and rollbacks, reads and rollbacks, reads and rollbacks. And it does improve the efficiency of our algorithm quite a bit. So now we've got a way to generate our tables, and we've got a nice simple algorithm we can implement. And again, once somebody's given us the DFA for our language, all we have to do is run our scanner generator on it, let it produce the tables, and run our code on those tables, and we're done. All right, that is a good place to leave this one. Next time we'll look at a direct coding approach.